Well, now it's time to carry out some measurements to understand the measurement techniques in optical fiber. When we have an optical fiber, usually the optical fiber is having core diameter which is 10 micron and cladding diameter 125 micron. This is single mode fiber, and a multimode fiber may have a core diameter 50 micron and cladding diameter 125 micron. So, this is multimode fiber, and then there is acrylic coating. So, the overall diameter might be 200 micron or 250 micron. So, if we look at this fiber, by just looking at it, we cannot make out whether it is single mode fiber or it is multimode fiber. We cannot say what is the numerical aperture of the fiber, what is the cutoff wavelength of the fiber, at what wavelength it will behave as single mode, at what wavelength it will behave as multimode, what is the losses of the fiber. So, when we have a fiber, we need to know all these things, we need to actually characterize the fiber. So, in order to do that, there are certain techniques, and I will discuss in this lecture few such methods. First of all, to distinguish between a single mode fiber and multimode fiber, of course, it has to be at certain wavelength. So, what you could do is you just launch light of that wavelength. If, for example, if you want to know whether the given fiber is single moded or multimoded at 633 nanometer wavelength. So, you can take a laser at 633 nanometer wavelength and launch light into it and observe the output. If you see in the output a speckle pattern, then it is a multimode fiber. If you see a clean Gaussian kind of pattern, then it is a single mode fiber. So, in this way you can make out whether a fiber is single moded or multimoded. What about the other parameters? Let us look at them. So, in this lecture we will understand the measurement methods for measuring numerical aperture, refractive index profile, mode field diameter, transmission loss, band loss, and cutoff wavelength of the fiber. So, let us first look at numerical aperture. We know what numerical aperture is. It basically signifies light launched at what angles would be guided through the fiber. So, there is a maximum acceptance angle. So, light launch only in this cone will be guided, and correspondingly at the output end the light will emerge out of the fiber into this cone. So, in order to find out the numerical aperture of the fiber, what we need to do, we need to measure this angle I max in the output end, at the output end of the fiber. And if we can measure this angle I max, then we can find out the numerical aperture of the fiber by simply taking sine of this I max. So, this method is very simple, but this can be used for only multimode fibers. So, you take a multimode fiber and use a white light source, and using this white light source you launch light into this fiber using a microscope objective of sufficiently high numerical aperture. This microscope objective simply works as a lens. So, with the help of this you launch light into this fiber, and you also put cladding mode strippers in order to strip off light which is going into cladding modes. otherwise there would be measurement error. Then otherwise at the output end you will collect light not only coming from the core modes, but also from the cladding modes, and numerical aperture is defined with respect to the guided light. So, it is essential that you strip off these cladding modes. So, you can use cladding mode strippers, which is nothing but you can put an index matching liquid onto either input end or output end, or at both the ends of the fiber. So that your cladding modes are stripped off. For white light source you can use a tungsten halogen lamp which has very broad spectrum. And why do we want to use a white light source? It is because with the help of white light source you can overfill the numerical aperture of the fiber. What do I mean by that? It is if you have a fiber like this and this is the cone of guidance. So, in order to fill this completely, you can use a white light source, so that this forms a continuum. Otherwise, you have guided modes which are discrete. So, in order to completely fill this numerical aperture, you should use a white light source. Also, if this is IMAX, then you should use a lens of sufficiently high numerical aperture. So, the microscope objective or the lens should have numerical aperture which is larger than this, which is larger than the numerical aperture of the fiber. So, we will have to ensure that. Now, what you do at the output end, the light emerges out in this cone and you put a detector on rotating stage which is rotating about this end of the fiber. So, this end should be at the center of the rotation stage, and then you move this, you rotate this pinhole detector about this center, about this end of the fiber, and at different angles you can scan the intensity or the power. So, you measure power at different angles. Your pinhole detector should have a hole which is very small in order to have good resolution. So, when you do this and you plot P as a function of theta, you will get a variation something like this. Now, the question is, where is this boundary? I need to find out this Imax, and Imax corresponds to the boundary here, the boundary of the cone, the semi vertical angle of the cone. But when I see this, it does not drop down to 0 abruptly, but it slowly goes to 0 and it will be 0 at theta is equal to infinity, for example. So, we have to stop, we have to define this boundary. For that, usual way is that you draw a line which corresponds to 5% of peak power. So, whatever power is here, you take 5% of that and get this line, and then find out what is this angular width. If this angular width is 2 theta e, then your Imax is theta e, and then you just take the sine of this and this will give you the numerical aperture. So, in this way you can measure the numerical aperture of the fiber. Next is, if you have a multimode fiber, usually a multimode fiber has dimensions 50 by 125 micron, and for local area networks you have a fiber which has nearly parabolic index profile. If you want to find out this refractive index profile of the given fiber, then you can use a method which is known as transmitted near field method. So, if the fiber has a refractive index profile given by this, that is n square is equal to n square 0 times 1 minus 2 delta f r in the core, and n square 0 1 minus 2 delta in the cladding, where delta is the relative core cladding index difference. And you remember the definition of delta. Delta is n1 square minus n2 square over 2n1 square, and fr is the profile function. It tells you whether the fiber has refractive index profile if this is r and this is nr or n square r. So, this is core cladding interface r is equal to a, this is the cladding refractive index, let us say it is n2. Now, in the core, whether the refractive index is this or whether the refractive index is this, it is defined by this function fr. For a power law profile, this fr can be written as r over a to the power q, this we had seen earlier also. Q is equal to 1 corresponds to this triangular profile, q is equal to 2 corresponds to the parabolic profile. So, fr is the profile function, and then it can be shown that if all the modes of the fiber are excited equally, then the near field power distribution PR can be given by this. What do I mean by near field distribution? Near field distribution means you launch light into the fiber, and at the output end you capture the light coming out of the fiber as it just comes out, very near to the fiber, very close to the fiber, so that the Fresnel number is much smaller than 1, that is the distance from the fiber is very small, within a couple of millimeters. So, the near field power distribution is given by this, and then if I am able to measure this near field distribution, then from this near field distribution I can find out the refractive index profile Fr. So, how do I implement this? Again I take light from white light source, which is tungsten halogen lamp, use a 20x microscope objective which has sufficiently high numerical aperture, then I launch light into this fiber using this and put cladding mode strippers. Then at the output end I use a 40x objective whose focal length is very small, about 2 millimeter or less, so that I can capture light from the output end as it just exits. Okay, I do not let it propagate. If I let it propagate, then whatever I will capture would not be the near field, but it would be the diffracted pattern. So, it would be the far field. So, I capture the near field and I image that near field onto this pinhole detector. So, what I will have a spot like this. I will have a spot like this, and then with the help of pinhole detector I scan the intensity across a diameter, which is given by this PR. So, PR is the intensity distribution, near field intensity distribution. When I plot it, it comes out like this. So, on either side of the center the intensity decreases, and what I see that at the center I have a small dip. This small dip is because of germanium out diffusion when the preform is collapsed. When you raise the temperature to a very high value and to collapse the preform, then there is germanium out diffusion, and because of that there is a small dip at the center. So, I can just correct it by extrapolating it or interpolating it like this, and then of course I can correct it by leaving these points and extrapolating these. Well, with the help of this, now I can immediately find out what is PR over P naught and then FR. So, while doing this measurement, again I should ensure overfill launch conditions, that is the numerical aperture of the lens which I am using here is larger than the numerical aperture of the fiber, and I use white light source to fill the complete mode volume, and I also should ensure that I am capturing the near field. What are the limitations? The limitations of this method are the measurement resolution is primarily limited by fiber Na, and there might be some leaky modes propagation. So, the light which is going into leaky modes also contribute to this PR. And another very important one is that this whole method is valid only when all the modes are equally excited. So, I should ensure that. Then another important parameter of a fiber, particularly of single mode fiber, is mode field diameter. So, the first two parameters were for multi-mode fiber, and this method is for a parameter of single mode fiber, which is mode field diameter. So, I know that for a single mode fiber the fundamental mode can be very well approximated by a Gaussian, and what I do in this method, as this Gaussian mode comes out of the fiber, I let it propagate over a small distance, and what I see then is the far field. I let it propagate maybe a centimeter or two, so that I am in far field a couple of centimeters. So, when this Gaussian exits from the fiber end and propagates in free space, so it is diffracted, and since it is a Gaussian mode, then diffraction of a Gaussian beam is another Gaussian. So, in the far field, if I scan the intensity along a theta, then psi theta is given by psi 0 square exponential minus 2 sin square theta over sin square theta f, where sin theta f is lambda naught over pi w naught. This can be shown by diffraction of a Gaussian beam. Now, this theta and theta f, they are very small. So, I can approximate this by psi 0 square exponential minus 2 theta square over theta f square. So, from here I can immediately see that theta f is the angle where this intensity, because mod psi square is corresponds to intensity, where the intensity falls down to 1 over E square of the intensity at theta is equal to 0, and at theta is equal to 0 you have the maximum intensity. So, if I am able to measure this theta f, then I can find out the mode field diameter by this. which is 2 lambda naught over pi sin theta f, which comes from here itself. So, the problem only reduces to measure the specular intensity distribution in the far field. So, for that I take a single mode fiber, launch light, laser light into this using a microscope objective. Again I use cladding mode strippers to strip off whatever light might go into the cladding modes, and then I let the light come out, propagate over a small distance from the fiber, and then I scan again the intensity at different angles using a rotating pinhole detector. When I plot it, it looks like this, and then to find out theta f, I draw a line which corresponds to P0 over E square, where P0 is the peak intensity here, and I measure this angular width. This is 2 theta f, and from here I can get df, which is the mode field diameter. Then I also need to find out what is the loss in the fiber. For this the method is very simple. You again launch light into the fiber from a laser using a microscope objective. You take a long fiber, it might be a kilometer long fiber, and identify one point very near to the input end, mark it, and from that point you might know what would be the length of the output end. So, this length should be known, and then you measure the power at the output end of the fiber using a photodetector, and let this power be P1L. Now, what you do, you cut the fiber here where you had marked it at point A, and remove this and put your pinhole. It is not pinhole, you use the photodetector, it is large area detector, so that you can collect all the light coming out of the fiber. Now, you measure the power here, and while you do this you ensure that the input launch conditions are not disturbed at all. Now, when you measure power here, let us label it as P10. Then by taking the ratio of this P1L at P10, I can find out what is the loss. So, the loss in dB per kilometer can be defined as 10 over L, where L is the length of the fiber in kilometers, times log P10 over P2L. It should be P2L, it should be P10. So, by measuring the power here and by measuring the power here, you can find out what is the loss coefficient. Then what is the bend loss? Because when you install this fiber in the field, you have instances where you need to bend the fiber. So, it is important to find out the bend loss of the fiber also. For doing this, what you do, you take a fiber and keep it straight and measure the power P1, and then what you do, you identify 2 points near the input end and output end of the fiber, which are almost 1 meter away from these input and output ends, and clamp them here. Then you make a loop of radius r here. You can make a single loop, or to have sufficient change in power you can make n loops. You can make n turns of radius r, and then you measure the power here. Let this power be P2. Now, what is the length in this bent fiber? Length of the bent fiber is 2 pi r times n, and so the bend loss can be calculated now as alpha b again in dB per kilometer. If you express this L in kilometers, is equal to 10 by L log P1 over P2. So, with the help of this you can find out the bend loss. You can change the radius and then see what is the effect of bend radius on the bend loss, and when you plot this it looks like this, where this bend radius is in centimeters and this bend loss is in dB. So, when the bend radius is large, that is it is not a tight bend, it is a big loop, then the loss is 0 dB, there is no loss, and as you make the bend tighter and tighter, you see that the loss increases, and around this value if you make it very tight, the bend radius is even smaller than or close to 1 centimeter, then the bend loss increases drastically. The last parameter that I would like to discuss here is the measurement of cutoff wavelength. I know what cutoff wavelength of a fiber is. It is basically the wavelength at which LP11 mode is cut off. That is, if lambda c is the cutoff wavelength, then for all the wavelengths longer than lambda c, the fiber is single moded, while for all the wavelengths smaller than lambda c, the fiber is multimoded. And this lambda c is given by this for a step index fiber, it is 2 pi a times square root of n1 square minus n2 square over 2.4048, but this is theoretical. Practically there might be several perturbations, it might be micro bending, macro bending, twisting. So, because of that the fiber effectively becomes single moded somewhat below lambda c, and this wavelength is then called effective cutoff wavelength lambda CE. So, what you can measure is lambda CE and not exactly lambda c, but it is very close. How do you measure it? This is recommended by ITU, International Telecom Union itself. So, you measure it through bending technique. How does it work? If you have you launch light into the fiber using a broadband source, maybe white light source, and then measure the band loss at different wavelengths, okay, and then see how does it work. So, if I am operating at wavelength which is equal to lambda CE, then large fraction of guided mode power is in the cladding mode, and if you are slightly greater than lambda CE, then only LP01 mode is guided and is well confined in the core, because then most of the power is in LP01 mode, all the other modes are not guided, while here the power is going into LP11 mode also, and it extends to the cladding also, and also because this wavelength is shorter than this, then LP01 mode power also goes into cladding. Now, if I decrease lambda below CE such that V is greater than 2.4048, then it should be greater than 2.4048, then LP11 mode would also be guided, but it is close to cutoff. You see, if you remember how does it work, if you look at BV curves of fiber, step index fiber, then you have this is V, this is B, this is LP01 mode, and this is LP11 mode. This point is 2.4048 and it corresponds to, let us say, lambda C or lambda CE. So, when your lambda is decreased below CE, that is V is slightly greater than 2.4048, then this is also guided, but it is close to cutoff. So, the power goes into LP11 mode, but a large fraction of LP11 mode power is in the cladding, and this power which is in the cladding is very susceptible to bending. It strips off very quickly when you bend the fiber. So, if you now bend the fiber, then there would be high transmission loss at this wavelength. If you further decrease lambda, then this LP11 mode would be very well confined, and then most of the power will now confined in the core itself of LP11 mode also. So, the band loss will decrease. So, what I expect is that if I start decreasing the wavelength, then at longer wavelengths, because most of the power in all the modes is in the core, so it is less susceptible to bending. So, I will have low band loss. As I decrease the wavelength, the band loss will increase, and when I keep on increasing and when I am near the cutoff, okay, then it will start increasing like this, and then if I keep on increasing it, then the band loss will keep on increasing, but further increase in lambda will result the power confinement only due to LP01 mode, and then it will decrease, because LP01 mode is less susceptible to bending, because if most of the power is in the core. So, I expect a peak in the loss curve. So, how to now find out the cutoff wavelength? I make an experiment like this. I launch light into the single mode fiber using white light source, which is tungsten halogen lamp again, using a microscope objective. I strip off the cladding modes, and then I make a loop, a big loop of 14 centimeter radius, which does not cause large bending loss, and then I measure the power here, okay, at certain wavelength. Okay, I can change the wavelength and I can measure the power as a function of lambda, and I change the wavelength with the help of monochromator. So, basically I pick particular wavelength using a monochromator, and then I measure this P1 lambda. Then what I do, apart from this, now I make a small loop of radius 3 centimeter, which can cause a large bending loss, and then again I do the same measurements and I measure the power P2 as a function of lambda. Then this ratio of P1 lambda and P2 lambda can give me the band loss, can give me the cutoff wavelength. I will show you how. So, if this ratio in dB is R lambda is equal to 10 log P1 lambda over P2 lambda, then I plot this ratio, when I plot this, then it looks like this. So, at longer wavelengths I have low bending loss, and when I keep on decreasing this wavelength, then around this wavelength it starts increasing, because now the power goes into LP11 mode, which is spread into the cladding, and then further decrease in the wavelength will increase the band loss, and after that all the modes are confined in the core. So, bending loss will decrease. Now, if I identify a point here which is 0.1 dB above this long wavelength edge, then this wavelength here will give me the cutoff wavelength. So, using this I can measure the cutoff wavelength. So, with this I complete discussion on measurement techniques in optical fibers, and in the next lecture I would summarize the key points which we have learnt in this course, and I will also give you what are the future trends, what are the specialty fibers coming up, and where we are heading in fiber optics. Thank you.